Hi everyone, welcome to our third lesson in our unit on astronomy. I hope that I have been blowing your mind at least a little bit in the previous two lessons already. If not, we're gonna keep on stretching your mind today. So today we'll be talking a little bit about the universe as a whole. So we'll start off by talking about more research into stars, specifically focusing in on how do we figure out the distance that separates us from various stars and other cosmic objects, because they're really far away. How do we figure out exactly how far away they are? And then based on some of those data and some of the things that we've been talking about over these past three lessons, we'll be able to start making some claims about the universe as a whole and how it's changing over time. So let's do it. Okay, so I don't know if you're sick of seeing this image yet, but you know, too bad, whatever. So there are lots of stars out there. They vary on a variety of different characteristics, and we've talked about most of those, at least a little bit, in the previous two lessons: color and temperature and size and brightness and age and composition. The last one then for us to talk about is their distance away from Earth. But before we dive into that, we need to do just a little bit of review of some key concepts from previous lessons so that you're able to access this new information and make sense of it when we're talking about the distance between us and these other stars. All right. So last time we introduced the idea of spectra. We talked about how each element has very specific wavelengths that are special for that element because each of those wavelengths have the right amount of energy. If we're talking about photons, that is, those wavelengths of photons have the right amount of energy to allow electrons to jump up an energy level. Okay, so there are these spectra for individual elements, these wavelengths that are really important for those elements. And then similarly, stars have their own absorption spectra. There are wavelengths that are mysteriously absent from the light that they are emitting and sending over to us. And so then we can figure out the composition of a star by kind of matching up the special wavelengths, the spectra of individual elements, with the spectra of the stars. And where we see matches, that's an indication that that star contains that particular element. Okay, so let's look at a couple spectra at this point then. So here is the absorption spectrum for our sun. Okay, so again, this is kind of showing us, so we can kind of think of if this is almost like a graph, that the horizontal axis here just represents different wavelengths of light that the sun is sending to us. And the sun sends a wide variety of wavelengths of light, but there are a few particular gaps, wavelengths that are not represented and are not sent to us as much as the other ones are. And so we see these very particular little dark bands at those specific wavelengths that are missing from the sunlight. Okay, so that's our spectrum from our sun, happy, like sort of middle-aged, main sequence, average mass kind of star. All right, and then here's another absorption spectrum from this supercluster of galaxies. Take a moment just to compare these two spectra. You should notice something kind of interesting as you compare the two of them. So what I'm seeing looking at this is that both spectra have really similar patterns to them. We see, you know, patterns of a bunch of lines over on the left, and then a gap, and then one, and then a gap, and then two, and another one. So they follow the same sort of pattern. It's just that the BAS 11 one seems to be all shifted over to the right, where the red wavelengths are. So we might call that redshift. Okay, so both spectra are really similar to each other, which kind of indicates to us that maybe they're similar sorts of objects, that maybe they have similar compositions, but it's just that this distant supercluster, everything's kind of shifted over towards the red wavelengths a little bit more. Now, what does that mean? And you'll have to reach way back into last unit when we talked about the Doppler effect. What is the significance of the fact that that the spectrum is redshifted? All right, so Doppler effect as a reminder, basically says that the wavelengths that we perceive for an emitted wave are changed a little bit, are altered depending on whether the source of those waves is moving towards us or away from us. So objects that are moving away from us, the waves that they're sending out end up getting kind of stretched out, and so the wavelengths look longer to us than they were when they were first emitted, which means that they're shifting over towards the red side of the spectrum, whereas objects that are moving towards us, they're kind of squishing and compressing those waves together so that those wavelengths appear shorter and bluer if we're talking about light. So really what this tells us is that this distant supercluster of galaxies is just moving away from us, and that's why the spectrum must be redshifted. We assume that maybe it actually produces a spectrum really similar to the sun's because they're so similar, they follow such similar patterns, but it's just moved over a little bit because those waves are getting stretched out as that supercluster moves away from us, which is kind of weird, all right? And the more dramatic that shift is, the more our wavelengths are pushed over on our spectrum, the more quickly that object is moving away from us. Okay, hang on to that information. That's going to be really important. We're going to circle back over there, but just wanted to do a little review up front. Okay, so we are trying to figure out then how to determine the distance between us and various stars. And there are three big methods that tend to be used at different scales. And this video is just, it's so good. So I'm going to let it go for a little bit. I'll let you watch that. And then I'll come back and just kind of recap and dig into a couple things. All right, go watch.
So the universe is absolutely huge. And to me, it's really amazing that we're able to look up from this tiny little planet and actually measure the distance to things which are so incredibly far away. Imagine yourself driving down along a road and looking out the window. Fences by the road seem to rush past really quickly. More distant trees seem to move more slowly, and distant mountains seem to barely move at all. This is due to something called parallax, and we can use it to measure distances. Say you wanted to know how far away a tree was. You could stop the car and take a picture of the tree with the mountain in the background. If you drove down the road and took another picture, you'd see the position of the tree shift relative to the mountain. If you knew how far you'd driven along the road, you could then do some simple maths to work out how far the tree was from you. This is how we measure the distance to the nearest stars. Instead of traveling down the road, we use the movement of the Earth as it orbits the Sun. In observations taken 6 months apart, the positions of nearby stars will shift relative to more distant stars in the background. And we can use the same geometry to work out how far away the nearby stars are from us. But the vast majority of things in space are much further away. Like the mountains in our example, they don't appear to move at all. So how do we know how far away they are? Imagine that you're walking around Greenwich Park at night, and you see a light. If the light moves away from you, you'll see it appear to get dimmer. And if it moves towards you, it will appear to get brighter. If you know exactly how luminous the light is, say it's a 40-watt bulb, you can use how bright it looks to you to work out its distance from you. And you can do the same for any other 40-watt bulbs. But other types of light could either be dim and up close, or bright and far away. Only objects of known luminosity, called standard candles, can be used to measure distances. There are lots of different things in the universe that we use as standard candles. For instance, Cepheid variable stars get brighter and dimmer in a regular way that tells us how luminous they are. So we can work out their distance, or the distance to a galaxy that they live in. But there are limits to using standard candles. What if something's in the way, blocking some of their light? Or what if you want to know the distance to a galaxy that has no standard candle? Imagine a fire engine. Its siren emits sound waves. As it rushes along the road, the crests of the sound waves in front of it are closer together than those behind it. Since the distance between the crests of sound waves determines pitch, the engine sounds higher as it approaches and deeper as it moves away. This is due to something called the Doppler effect, and it affects light waves emitted from moving sources too. Now shorter waves appear bluer, and longer waves appear redder. We can use this blue shift and red shift of light to study the motions of things in space. Looking at galaxies containing standard candles, astronomers found that the light from all distant galaxies was redshifted. The more distant the galaxy, the greater the redshift. We now understand this is because our universe is expanding. From our viewpoint, all distant galaxies seem to be moving away from us because the space between us and them is stretching out. More distant galaxies appear to recede faster because there's more space between us to expand. Light waves traveling to us from distant galaxies are redshifted, not because they're moving away from us, but because they've been stretched out as they traveled to us through our expanding universe. We know how far away things are in the distant universe by measuring how redshifted their light is. What's most incredible to me is how all these measurements build on each other. It's only by knowing the scale of our solar system, the distance between the Earth and the Sun, that we're able to measure the distances to nearby stars using parallax. If we can learn how far it is to some nearby standard candles using parallax, we can then use comparison between standard candles to measure the distances to farther stars and galaxies. Finally, by studying the motions of galaxies with standard candles, we learn we can use redshift to measure distances throughout our expanding universe.
All right. So let's go ahead and recap some of those ideas from that video. So the first method that astronomers use to determine the distance between us and specific objects out in the night sky is parallax. And parallax is basically just using geometry to try to figure out where everything is oriented in space based on how its image from our perspective kind of shifts over time. And hey, AP Psych students, you know this same idea as the monocular depth Q of relative motion. So just, cross-curricular connection there. Okay, so here's the idea with parallax. We know that we are moving within the universe as we orbit around the sun. That's a very predictable movement that we are going through. So we're not staying stationary. We are moving around. And as we move through our orbit from one side of the sun to the other, we end up seeing things looking a little bit different. Certain stars don't appear in the same location in the sky that they did 6 months ago when we were on the other side of the sun. All right. And this is the basis of, constellations and all sorts of things. Right. And so what we can do is kind of keep track of, well, how different does the apparent location of a star look in the night sky when we move around to the other side of the sun? And so the more drastically the object seems to move from our standpoint, the more what it must be. Right. So the bigger the change in the apparent location of a star, the more it seems to move relative to the background of the night sky, the closer that object must be. And you can experience this just like stick your hand in front of your face. If it's really close and you move your head a little bit, your hand looks like it moves a lot with respect to, your face. But if you put your hand far away and you move your head the same amount, your hand doesn't appear to have moved as much. Okay, that's the basic idea of parallax. If things don't appear to be moving much over the course of a year, they must be really far away. If they appear to move a lot, then they must be pretty close. Okay, so this works really well for relatively nearby celestial objects. All right, now if we want to start getting a little bit farther away, the next thing that we can start looking at is standard candles. So through parallax, astronomers started identifying these patterns, these particular types of cosmic objects that had very consistent luminosities. All right, that they would use parallax to determine where they were, and then they would sort of say it seems like even though these are in different locations and they look a little bit different from our perspective, once we correct for their distance, they're the same brightness, okay? And so what the astronomers realized is that for these objects that have a known luminosity or a known brightness, the dimmer it looks from our perspective, the farther away that object must be. And again, this just kind of makes sense. If you have a flashlight and it's right here in front of you, that's really bright. But if you move it away like a few hundred feet, then it doesn't seem nearly as bright because that light has spread out over a much larger space. And so if we have a few objects where they have very consistent brightness no matter where they are in the universe, we can then kind of use those to gauge, okay, well, how far away is this whole galaxy that contains the Cepheid variable, for example. Right. So that's another method that we have available to us. It can get us a little bit farther away and measure distances a little greater than parallax can. All right. Now let's come to our third method. This one's my favorite. This brings us to Hubbles Law. All right. So back in the 1920s, all the things that we've already talked about had already been established at this point. We were using parallax. We were using standard candles. We were familiar with the idea of redshifted or blue-shifted spectra. And so we have a scientist named Edwin Hubble who decided to gather some information about a bunch of different galaxies, determine how far away they are, and how fast they must be moving based on how redshifted their spectra are. Okay, so we use standard candles and well, mainly standard candles because it was pretty far away. So we use standard candles to figure out the distance away that various galaxies were. And just so you can make sense of this table, the unit used to measure distance here is megaparsecs. And megaparsecs are equal to about 3.26 million light years away. Okay, so that's really far. So even the closest galaxy here, NGC 0055, the fact that it's 2 megaparsecs away means that the light that we see from that galaxy was actually emitted 6.5 million years ago. And that's just the closest one. All right, so okay. So that's the distance based on standard candles. And then again, he looked at the spectra, measured the redshift, and from that determined how fast those galaxies must be moving. With respect to Earth. Now, take a moment, look over this data table, choose a few particular points, and try to figure out what is the pattern, what's the relationship between the distance away, how far away an object is, and how fast it appears to be moving. All right. So again, I always like to start with just like a pair of data points. So like ignore the whole table except for these 2 points, all right? So one galaxy is 2 megaparsecs away, the other one is 4 megaparsecs away. That's a difference of about a factor of 2. So going from 2 to 4, that's about doubling the distance. And then if we look at their relative velocities as well, one is 90 kilometers per second and one's about 180 kilometers per second. So I see that if I double distance, I'm doubling velocity as well, okay? Or if I choose these 2 data points right here, if I triple the distance from 2 megaparsecs away to 6 megaparsecs away, the velocity goes from about 90 to about 270 kilometers per second, so that's about tripling. So I triple the distance, I triple the velocity. Or, just for fun, let's jump down to the bottom of the data table as well. I choose maybe 20 megaparsecs and 40 megaparsecs. So again, a pair where one is double the distance of the other, and I see that the velocity similarly is about double when we look at that. So going from about 1900 kilometers per second to about 3800 kilometers per second. So given that whatever factor my distance changes by, my velocity changes by that same factor, that kind of points to a linear relationship. And sure enough, that is what Hubble found. And just take a moment to appreciate this is the actual graph that was in the 1929 paper that Hubble published. And like they didn't have computers back then. This is all done by hand. Isn't it cute? Oh my gosh. All right, anyway, so Hubble determined a couple really important things from his data. First of all, he determined that all the spectra were redshifted. Nothing was blue shifted. Things aren't moving towards us. We're not like in the middle of like a huge cosmic collision, at least nothing, major. But in fact, everything is like leaving us. Everything appears to be redshifted compared to known elemental atomic spectra. So that's interesting. And then secondly, we see this linear relationship between the distance away that a galaxy is and its velocity, which means that we can use redshift and determining how shifted a spectrum is to ultimately figure out how far away it must be by kind of seeing where it falls on this Hubble graph. So that's kind of cute. All right. Now let's take a moment to talk really quickly about like this whole everything's moving away from us. And it's not because we're like the pariahs of the universe and everything is like get away from Earth as quickly as possible. It's not personal. What we believe is happening is that rather than it being a weird coincidence that everything just happens to be moving away from us, scientists speculate that probably what's the case is that the universe is expanding. It's not so much that objects are moving away from us, so much as the space in between us is getting bigger. And the analogy that's often used is imagine the universe as being like a balloon. Okay, and if you take a balloon that's only partially inflated and you use a marker to draw two dots on it, they're a certain distance apart. And then if you were to then inflate the balloon, those two dots are going to be farther apart, not because the dots moved themselves, but because the balloon as a whole is bigger than it used to be. And so similarly, it's not really that everything is going out of its way to move away from us. It's that the very fabric of space in between us is getting bigger in and of itself. So cool. All right. Anyway, one more thing I really want to dive into here. It's going to get a little bit mathy, but I swear the payoff is good. So hang with me here. Okay. So, coming back to Hubble's graph here. Okay. So we've established linear relationship between the distance and the velocity of a particular galaxy. All right. Now, the slope of that graph has a special name. We call it Hubbles Constant. And it's basically kind of just giving us a measure then of the rate at which the universe is expanding, because it's telling us then how quickly things are moving away from us as a function of their location with respect to Earth. Okay, now if we use our good old just like y equals mx plus b slope intercept form, that gives us this equation of velocity, the variable on our vertical axis, is equal to the slope, Hubble's constant, times distance, which is the variable on the horizontal axis. Okay. Now, the thing is, this isn't our first time looking at an equation that relates velocity and distance in a linear fashion. If we rewind way back to the beginning of the year, the very first physics formula that we talked about was this idea of velocity is equal to displacement or distance, if things are just moving in one direction, over time. All right, so we've already seen a linear relationship between velocity and distance before. And we can rewrite this equation as velocity is equal to 1 over time times distance. Okay, the same way that like 3/4 is the same as 1/4 times 3. I can kind of just separate those two things out. Okay, so this was our first equation in the very beginning of the year, way back in like August and September, we were talking about this, okay? Now we've just established that from this graph, Hubble's law says that the velocity of a galaxy is equal to Hubble's constant times its distance away. So if we compare Hubble's law, this new equation here, to that second form of the velocity equals 1 over time times distance, those are really similar equations, and they end up being exactly the same if Hubble's constant is equal to 1 over the amount of time that all these galaxies have been moving away from us. Or in other words, Hubble's constant is equal to 1 over the amount of time that the universe has spent expanding. Okay, a little weird. You still with me? Still with me? We're just setting those two equations equal to each other. That's it. All right, so given that Hubble's constant, the slope of this graph, is equal to 1 divided by the amount of time that the universe has been expanding, we can just like invert both sides of that equation and determine that the amount of time that the universe has been expanding is just equal to 1 over the slope of this graph. And when we plug in the slope of this graph and take the reciprocal of it, we get 14 billion years, which is the age of the universe. Whoa. All right. So what this means is we have piece by piece over the course of centuries here, gone from using geometry to try to figure out like how far away the moon is and things like that, and slowly building upon that knowledge using parallax and then to standard candles and talking about spectra and redshifts and these linear relationships and Hubble's law to eventually being able to figure out how old, presumably, assuming all of these patterns have been holding up, how old the universe is. So that's kind of wild. Anyway, let's just check in on your understanding. So we've got 3 different absorption spectra from 3 different stars here. Now the one on the bottom is from our sun, nice and close to us. And then the other 2 are from 2 other stars, star A and star B. Taking a look at these spectra, what can you determine about how far away star A and star B are from us? Which one must be farther away? Hubbles law tells us that the farther away an object is, the more redshifted its spectrum is going to be. And so star B, we see, must be farther away because its spectrum is shifted more dramatically over to the right, towards the red side of the continuum than star A's is. So since it's more redshifted, we know that it's experiencing a greater Doppler effect, which means it must be moving faster, and if it's moving faster, it must be because it is farther away from us, and there is more space between us to be expanding and driving that motion, or apparent motion, away from us. Okay, that was a lot of mind-bending stuff, but thanks for sticking with me. Hopefully I gave you a few things to, ponder as you go through your day. As always, ask me your questions. I am eager to look at them and to respond to them in Edpuzzle. That is all, folks. I love you very much, and I hope you have a wonderful day. I'll see you next time.